Okay guys, hope you're all safe and well. We're going to move on looking at the C4 calculations topic now. Last week we looked at percentage yield, which was the actual yield of product, i.e. how much you got at the end divided by the theoretical, which is what you should have got based on calculations. And we discussed the reasons why it's difficult to get 100% yield, things like reversible reactions, impurities in the reactants, side reactions, and so on and so forth. A really important measure percentage yield is in terms of whether we want to take a reaction from the lab and do it in industry to make millions and millions and millions of tons of it. Another important measure is this thing called atom economy, and this is the actual what atom economy is. All right, it's a percentage, so there's times 100 in it. It's the relative formula mass of desired product, and relative formula mass is just the MR. We won't call it relative molecular mass of the desired product divided by the sum of the relative formula masses of all the reactants times 100. And that's taken straight from the GCSE Chemistry specification. It's quite wordy, and it looks a bit daunting, but it's more simple than you think. So I'm going to walk you through an example now, and then a couple of examples and set you off with some other questions. So have a look at this question here. It says, calculate the atom economy to form lead from lead oxide. So we need to find out what is lead in this particular, or where is lead in this particular equation. So let's have a look here. So lead on its own, Pb, is that. So that is our desired product. Yeah. So that's our desired product. So that's going to be, everything in that red circle is going to be the top part of this equation. So it's what we want, all right? It's our desired product from lead oxide. Now it says here we've got to divide that number by the sum of the relative formula masses of all reactants. And the key word there is all reactants. So this purple circle here is basically everything that's on the left of the arrow. All right, and that's how I do it when I'm doing these calculations. If I ever do exam questions for practice, I would always sort of like have two different coloured pens or two highlighters and just highlight what I need to actually figure out here. So let's now write a list of things that we actually need. So the first thing is the red circle. So in the red circle, what have I got inside the red circle? I've got one lot of Pb and nothing else. And in the purple circle over here, I've got one Pb, two O's, and then in total over here, I've got four H's. So H2 has two hydrogen atoms in it, and because there's two lots of it, I've got four H's in total. And then just stop and just make sure that every single atom in both circles has been accounted for. And if the answer is yes, you can then proceed with the next part. So now I need to work out the total masses of these things using the atomic masses on the periodic table, so the top numbers, if you like. So if you look at the periodic table, lead has a mass of 207. So one lot of 207 is 207. So there is my calculation for what's in the red circle. Over here then, lead is 207, oxygen is 16, hydrogen is 1. They're the top numbers in the element boxes on the periodic table. So I'm going to tally these up. That's 207, that's 32, and that's 4. Add those together, you end up with 239 plus 4 is 243. Yeah. So now I've got my two numbers. I can actually go ahead and calculate the percentage atom economy. So percentage AE, or atom economy. So it's the red number, which is 207, divided by the purple number, which is 243, and then times by 100. So I will now have a go at my calculator and see if we can't get this right. Okay, so let's have a look. So you've got 207 divided by 243 times 100, 85.2%. 85.2% is the atom economy there, which is a really high atom economy. So atom economy is really useful because it sort of lets you know what percentage of the total atoms you put into a reaction or total mass you put into a reaction ends up in the product that you want. Why is this important then? Okay, so I'll write down here a list of reasons why this is very important and then give you a second example to work through. Okie dokie. So I'll write down some reasons just here why a high atom economy is desirable. So high atom economy. Okay. Well, the first thing is you get more product. All right. So this tells us that 85.2% of the total mass of reactants we put in ends up in the product we want. So if we had 100 grams of reactant, we'd end up with 85.2 grams of the product that we want. So that's quite useful because it gives us more desired product. Another reason, by having more desired product, we actually end up with less waste. And that's very important, given how a lot of the things we're using are from the earth, which has a lot of, which most of the resources are finite, so they will eventually run out. So that's another reason, less energy. Okay, so you've got cheaper energy costs effectively. So again, if that number was say 40% or 42%, we would have to do this reaction twice to get the same amount. So that's why it's quite important, and that can be quite expensive in terms of energy costs. All right, and another one, it reduces pollution. So you get less carbon emissions. So there's less energy. Anytime you've got less energy, you reduce your carbon dioxide emissions, which means it's better for the environment because you reduce global warming. So that's why a high atom economy is desired. Okay, so you'll pause the video now. I'm going to clear the board and then I'll give you a second example to have a go at. Okay guys, I've got a second question here. It looks very similar because we're producing lead. All right, but I thought I'd show you a second possible equation we could use to produce lead. So it is a different equation, so it'll have a different atom economy. And then we'll use that value to compare it to the first example and see which one is better. So the key thing is with these questions is find out what your desired product is. So I've got my red pen ready because I need to find my desired product. So what am I trying to figure out? Calculate the atom economy for the production of lead. Production of lead. Product, right-hand side. And lead. Lead, which one's that? So it's going to be that one again. So there's my red circle. And then the reactants, dead easy each time, everything that's on the left of the arrow. And then once you've got your two colourful circles, then you can start making your list of atoms which are within each. So over here, we've got 1 Pb. Over here, we've got 1 Pb, 2 Os, and 1 C. And again, once you've done that, you can go to the periodic table, look at the different mass numbers, and start calculating the total NRs. So that's 207, 16, 12. So 207, 32, 12. And let's add them all together first. 239 plus 12 is 251. Okay. That's 251, and on this side, 207. Okay, so there's my red circle, and there's my purple circle. I can now go ahead and do the calculation. If you have made a mistake, as long as you've set out your calculation well, if you do make a mistake, you will get error carried forward. So you can still get marks for getting the wrong answer. So my percentage, atom economy, is 207, so it's red number first. Divided by purple number, it's 251, times it by 100. Okay, so get my calculator ready. There it is. So 207 divided by 251, 82.5%. Okay, so 82.5% was the correct answer there. Let's compare that to the first equation then. So the first problem was 85.2%, so very similar, but this one actually produces less of the product. So for every 100 grams of reactants, I'm getting 82.5 grams here. Up there, I'll be getting 85.2 grams of the product that I want, which means that this one, because it's lower, means I'm going to end up with less product, more waste, more energy costs, and more carbon dioxide emissions. Remember, higher atom economy is better because we get all these wonderful reasons. Now, so if I was going into business, just by looking at atom economy, I would say that the first method would have been the most effective or efficient for us. That's not the only thing to take into consideration, though. There are a few other things. Not only you have to consider percentage yield, you have to take into consideration whether the reactions are reversible. You have to take into consideration the cost of the reactants. You have to take into consideration the percentage yield as well, because don't forget, percentage yield and atom economy are two separate things. Percentage yield is how much you actually get at the end. Atom economy is a fixed value for each reaction. So the atom economy tells you what percentage of the atoms you put in end up in the product that you want. So again, just based on those two, I would consider the first method to be the best, but there are other things you need to take into consideration. Environmental impact's a massive one as well. So which one's going to have the higher energy costs? Because we might have to heat this one up to 300 degrees Celsius, but the first one we have to heat up to 700 degrees Celsius. All of a sudden, that's going to increase my costs, my energy costs. So it's quite it's a fine line, it's a balancing act, but like I say, atom economy is a good place to start for working out whether or not you want to take a reaction from the lab, the science lab where you guys have been working, to industry to make millions and millions of tons and therefore a lot of money as well. Right, pause the video, I'm going to clear the board and do another couple of examples with you. Okay guys, here's our third example. I'm going to get my red and purple pens ready. It says calculate the atom economy for the production of copper. So production of copper, I'm trying to produce copper here. So production on the right hand side. So which of these things is copper? It's that just there. And then we're going to be dividing that by all of the reactants. So it's everything on the left. Sorted. So let's go through the process again and just write down on each side which atoms are in your two circles. So I've got one copper there. On this side I've got one copper. I've got one carbon, 3 oxygens. I've got one H there, but again, it's two. I've got 2 lots of this whole chemical here, so hydrochloric acid. So 2 lots of H in total. And then 2 lots of Cl. So it's quite a big shopping list on the left-hand side. So let's do that first. Using the periodic table, copper has a mass of 63.5, carbon 12, oxygen 16, hydrogen 1, and then chlorine 35.5. So 1 times 63.5 is 63.5, 1 times 12 is 12, 3 times 16 is 48, 2 times 1 is 2, and 2 lots of 35.5 is 71. Right, so if I add up all of those things just there, okay, and I'll do it on my calculators to make sure that I don't make a mistake. So 63.5 plus 12 plus 48 plus 2 plus 71, 196.5. So that's my purple number for this calculation. On this side, what have I got in the red circle? I've only got 1 copper. Just be careful with some examples. There might be a big number at the front. If there is, make sure you include that in your calculation. So I've got 1 lot of copper, which is 63.5. So I've got my red circle, I've got my purple circle. I can go and work out the percentage atom economy. And then times by 100. So that's the calculation you end up doing. Like I say, you can pause this video at any point and have a go if you want. I'm just going to try and work out the answer. 63.5. %. Okay, so again, that's not the highest atom economy in the world. There are probably going to be much better reactions out there for generating copper, because that tells you that 32 for every 100 grams of reactants you put in, you're only going to get 32.3 grams of the product that you want. The rest of it is going to be waste products. How can you actually improve the atom economy? Well, rather than just selling the copper here, if we can somehow find a use for the water and the carbon dioxide, so we sell that and we sell that, all of a sudden, these products become desirable, so you end up with 100% atom economy. All right. I'm going to show you one more example. So pause the video, I'll clear the board, and then we'll have a look at it. Okay, guys, last one, and then I'll let you get on with the problems I've set you. So it says here, calculate the atom economy for the production of ammonia. So what am I trying to make? I'm trying to make ammonia. So it's everything in that circle just there. Divided by the sum of all the relative masses of the reactant. So it's basically same thing again. Everything in the red circle divided by everything in the purple circle. Some of you might have noticed that there's no need to do a calculation here, but we'll just try and prove that with the numbers as well. So in the red circle, I've got 2 lots of N. So just look there, I've got 1 nitrogen in NH3, but because I've got 2 lots of that molecule, I've got 2 nitrogen atoms. There are 3 H's there, but because I've got 2 lots of that molecule, I've got 6 H's in total. So I'll do the maths as well while I'm here. Nitrogen has a mass of 14, so 2 times 14 is 28. Hydrogen has a mass of 1, so 6 times 1 is 6. And you end up with 34 in total. Let's do the purple circle then. So in the purple circle, I've got 2 N's and I've got 6 H's in total. Yeah. So in total, I'm going to have 2 times 14, which is 28, 6 times 1, which is 6. Add them together, you end up with 34. Now you'll notice something here. What's in the red circle equals what's in the purple circle. So we already know what the atom economy is going to be. So it's going to be 34 divided by 34 times 100, which equals 100%. But the eagle-eyed out there would have noticed you didn't really have to do a calculation, because if atom economy tells you the percentage of the total reactants that end up in the product that you want as a mass, if you only have one product, then that is your desired product. There are no waste products. So effectively, if you've only got one product, your atom economy will always be 100%. So you don't need to do a calculation, and I hope that helps you out with the problems that I've set you. Okay.